So we were talking about multiple quantifiers and the negating sentences. Last time we didn't finish this section. When you have multiple quantifiers, so you want to negate a sentence with those multiple quantifiers, then you have to be careful how to negate a compound statement with those quantifiers. You would change the universal quantifier to existential quantifier and vice versa, and then negate the sentence. All right. Today we're going to finish this section and actually the whole unit today. So we'll start from greatest, the least elements. We're going to use quantifiers to define this greatest and least elements in a set. So let set S is contained in all real numbers. So S is a set with real numbers, a subset. And X is a real number, all right? It doesn't have to be in S when you write this, okay? Maybe in S, but may not. Okay, so we say that X is the greatest element of the set S if X is in S, and also for each Y in S, we have X greater than or equal to Y. So what is the greatest element of S if, of course, X has to be in S, and then it has to be greater than or equal to any other elements Y in S, okay. Similarly, we can define the least element of S if X is in S, and for each Y in S, we have X less than or equal to Y. So if X is less than all the other elements in Y, in S, all the elements in S. So we're talking about the real numbers, okay? In here. So since we used quantifiers, we introduced quantifiers, the two quantifiers. Then we can use those quantifiers to define the greatest and the least elements. So we can write the whole definitions of previous page into symbolic logic. So if X is the greatest element of the set S, then we can write, X in S. If you translate that definition in words into symbolic logic. So first, the X has to be an element in S, and then and, all right? For each Y in S, so for any arbitrary Y in S, X greater than or equal to Y. So this is the direct translation of the definition of greatest element from wording to symbol logic. And similarly, you can define the least element of S as, X is in S, and or conjunction or disjunction. I believe this is a disjunction, or this is conjunction, I guess. And also, for any Y in S, for each one is, so we can use the arbitrary or universal quantifier again in here. We have x less than or equal to 1, all right? So then, this is just the definition of greatest element of S and least element of S. But they may not exist, we're going to see some examples, that actually one of those or both do not exist. But if in case the set S does have a greatest element, then we would use the existential quantifier in the front. So there exists such a real number x such that this whole condition is satisfied. So the other thing is just the definition of the greatest element of S. Okay. So let's just make sure that S has a greater element. All right. And we can make it shorter since, we don't have to say X belonging to R. It's a real number by default. Okay, so we just say there exists X in S, so that for any Y in S, X greater than or equal to Y. So we don't have to write the conjunction here also. So that's the short notation or shorthand way to define the greatest element. And you can do the same thing for, or similar thing for greatest or least element in S in symbolic logic. Okay, so just make a formal definition of greatest than the least element. So we say that S has a greatest element. If there is some X in S, that is the greatest element of S, okay? And S is a subset of real numbers, all right? So this definition is a little different from the previous one in that, the previous one just defined what is the greatest element of S. Suppose it exists, but this definition then, defines what it means by saying that S has the greatest element, all right? And similarly, we say that S has a least element if there is some X in S, that is the least element of S, all right? So just one more step from the previous definition. So let's just do some examples. Suppose S is the set of natural numbers, so it's a subset of real numbers. All right. So obviously, this set does not have greatest element. You have all the all the positive integers, right? That's called the natural numbers. So it just keeps going. You can always add one, no matter how big the number is, to make it a natural number. So it does not have a greatest element, but that can be understood in a different way by using the symbolic logic. So that way is to negate the definition of S has a greatest element. Okay, so So we just talk about the definition of S has a greatest element. If we negate it, and then it will be easier to understand also. So what you do, you're going to change the universal and existential quantifiers. So this is the definition that S has a greatest element. All right. So when we negate it, we're going to change the existential quantifier to universal quantifier. So we say for arbitrary x in S, and change the universal quantifier in here to existentials. There exists some y in S. And then we need to negate the x less than or equal to y, so that will be x, x greater than or equal to y, so that will be x less than y. Okay, so when you negate this compound statement, you're going to change universal quantifier to the existential quantifier and vice versa, plus negate the open sentence. All right. So let's see what we're getting here then. If we do that, so that becomes that, as I just said, So it says for any x in S, there exists y in S such that x less than y. Okay, so remember, S is the set of natural numbers. So for any natural numbers x, natural number x, there exists another natural number y such that x is less than y. Okay, so if you are given a arbitrary natural number x, you can always find another natural number y such that x is less than y. And that is true because you can let y equal to x plus 1, for example, or x plus 2, right? You can always find such y. Given x, you can always find such a y, so that x less than y. So this statement is true, but this is the negation of the statement that S has the greatest element. The natural numbers has the greatest number. The negation of it is true. So the statement itself is false. So that means S does not have a greatest element, actually, or the natural numbers does not have a greatest element, right? So the natural numbers do not have a greatest element, but it does have the least element, that is 1. Of course, we know that the natural numbers start from 1 and then increase to 2, 3, 4, 5, and so on. So that's one application of the quantifiers. All right. So let's just define some more terms we're going to use a lot. We have talked about this before in Cal 2. If you took Cal 2, I assume you should. When we talk about the sequence and the series in the chapter of sequence and series. And these are the upper bound and lower bound. Okay. So let's start from a subset S of R. So that's a subset of real numbers. The upper bound for S is some x in R such that for all y in S, y less than or equal to x. So if you compare the definition of greatest and the least elements of a set S, the difference between that and the upper bound and lower bound here is this X does not have to be in S. It just say there is some real number. So it might be outside of S. Okay, but it could be in S also. So that's the difference. So upper bound is not necessarily in the set itself, but it will be greater than or equal to all the elements in the S. All right. Similarly, we can define lower bound for S if there is some real number such that all the numbers in S is greater than or equal to that number X. So the lower bound is less than or equal to all the numbers in S. All right. Correspondingly, you can say that S has upper bound if there exists some real numbers such that for all the numbers in S, they are less than or equal to this X. So that means, if there is some real numbers that is greater than or equal to all the numbers in S, all right? Similarly, we can, say S has a lower bound if there is some real numbers that is less than or equal to all the numbers in S, all right? So the first two definitions just defines upper bound and lower bound. Then the other two definitions just tell whether there is upper bound or lower bound. Okay, just like we did for the greatest and least elements. There's a little difference between those definitions. Okay, for example, let's say S is the set from numbers between 0 and 1, including 1, but not including 0. Okay, so we have open interval at 0 and the closed bracket at 1. So that's what it means here. You can also write in the set notation instead of interval. So that means X is a real number such that it's greater than 0 and less than or equal to 1. All right. So obviously S has a lower bound. For example, -1. You can see all the numbers between 0 and 1 is greater than -1, or -1 is less than any number in S. Okay, so that's a lower bound for S. But it's not unique. You can find many other lower bounds. For example, 0 is also lower bound because all the numbers in S is greater than 0, right? Of course, -3 is also lower bound. And you can find that, a lot of numbers, -2, -0.5, and so on. But the point is, it does not have a least element. It has a lower bound. You can easily find a lower bound, but it does not have a least element. It does not have a number in the set that is the smallest number in the set, right? You may say 0, but 0 is not in the set, and any number greater than 0 will be and less than or equal to 1 will be in this set, but you can always find another number less than that number. If you say 0.1, then you can find 0.01 less than 0.1. So 0.1 is not a least element. Similarly, 0.01 is not, and you can not find the least element in this set, right? The upper bound, on the other hand, you can also easily find the upper bound 1, 2, 3, 1.5, and so on. And this time, it does have a greatest element, which is 1. Okay, less than equal. So 1 is the greatest element, and it is upper bound, and it is in S. All right. So so everything can happen. So the last thing about this section is just a summary of the and negated sentences. All right. So we have 6 rules in here for negation that can be very useful, in symbolic logic when you try to simplify, the statements or sentences when you try to do some problems. So the first negated sentence is the negation of P is the same as P itself, right? So P is a statement or sentence. Okay. So the negation of a statement or a sentence is just the statement of the sentence itself, of course. Just two negatives make it positive. And the negation of the disjunction of two statements or sentences, P and Q, is the same as the conjunction of negation P and negation Q. All right. And similarly, the negation of P conjunction with Q is the same as negation of P disjunction with negation of Q. So these two equivalences are called De Morgan's law, if you still remember. And we talked about this also before, the negation of a conditional statement or sentence, P implying Q, is the same as P conjunction with the negation of Q. By the way, all of these equivalencies can be proved by the truth table. All right. So that's the direct way to prove those equivalencies. So logic equivalencies using the truth tables. You just list all the truth values for P and Q, and then find out the left and the right, and see they are exactly the same for different combinations of P and Q. All right. And the last two is just negation of statements with quantifiers we just talked about. So if you try to negate statements with a universal quantifier, so this px is just sentence, but with the universal quantifier, it becomes a statement. Okay, so what you do, you're going to change the universal quantifier to the existential quantifier and negate the sentence P. Similarly, if we try to negate a statement with existential quantifier with open sentence P, you're going to change the quantifier to universal quantifier and then negate the open statement also. So these are the summarized results we talked about. So this is the end of this section, and that's the end of the whole unit 2. So we finished the 2 units. So we're going to start a new unit next time, but we're going to skip the 2 units 3 and 4. If I just show you that, what we're going to do. Okay, let me just share this. Oh, I'm sorry. Okay, so this is the syllabus we had before. We finished them unit 1 set theory, and we just finished the unit 2 logic. And unit 3 is the theory of integers, and unit 4 is relations. And we actually, discuss those topics in that course 507. We talked about the divisibility, the extended Euclidean algorithm, prime numbers. We talk about relations, properties relations, equivalence relations, equivalence classes and partitions, integers, modular, and so we're not going to repeat the same topics in this course. So we just jump into unit 5 function, and then we're going to discuss some basic probability concepts. So the next is the unit is functions. You have learned the functions from Hardy algebra, I believe. But we're going to use functions in a more mathematical way, in a more formal definition from pure mathematics. Okay, and these are the topics we're going to cover. How to define functions in rigorous way, in pure math, and then we talk about injective and surjective functions, compositional functions, additional facts about functions. Those are all the facts we learned before, but we're going to introduce some new notions and do this in a more abstract way. All right, so I guess it's already 5:44, so I'm not going to start the unit 5. I'm going to stop here, and we'll just start the new unit on Wednesday.